This video is sponsored by Brilliant. More on that later. I recently went to the doctor. I said, "Doctor, I have a problem. My resource monitor, htop, says my program is using 2.5 gigabytes of memory, but my memory profiler, memusage, says it's only using 1 gigabyte of memory. I think I might be losing it." And the doctor said, "You're in luck. I hear the great Fastad is making videos now. Why don't you send him an email and he'll make an in-depth video about it? He might even make 2. And I said, "But doctor, thing is, I already made that video. I already explained everything that was going on with the program, and to another man, a lesser man, this might have been enough. But not me. Oh no, not me. Sure, I made diagrams of what I thought was happening, but what if I got it wrong? How can we be sure? Well, by making our own memory profiler in Rust that spies on everything the memory allocator is doing. That's exactly what I did, and this is what it looks like. It was a very interesting project, Rust on the back end, Rust on the front end, learned a ton about the Linux kernel while doing it, and I want to share that journey with you today. But first, I'm going to explain memory fragmentation with cars, the vehicle, not the movie. How many cars does it take to transport 40 people somewhere? Well, let's say every car can fit about 4 people, so maybe 10 cars? Wrong, because the average car occupancy is actually 1.5. So in practice, it's closer to 27 cars. That's a lot of wasted space. We can do better than that. I'm not talking about buses or trains. They don't exist in that universe. I'm talking about ride sharing. We can simply arrange for every car to fill up with 4 people before it leaves. No more wasted space, except some passengers get off at midpoint, leaving the cars, again, half empty. And this is fragmentation. We're taking up all that space with half-empty cars. And this is what happened with the program. The memory profiler is counting the passengers, or memory allocations, and the resource monitor is counting the cars, or memory pages. So I made a tool called mevi that visualizes memory pages, and we can now see clearly the difference between one version of the program that doesn't cause fragmentation and one that does. But mevi doesn't just show snapshots of the state of memory at a given point in time. It lets us observe changes in real time as the program is running without changing its behavior. Just like strace, it can help us understand a lot about what a program is actually doing and about how memory works on Linux in general. For any of this to make sense, we're going to need a bit of theory, just a bit. I need to make sure that we have the same mental model. Here's mine. Now the top half there doesn't always look like that. Different languages do different things, but the bottom half, no matter what, programs ultimately have to go through the kernel to ask for memory. I mean, we could not have a kernel and just have a single program. That's how it's done on some small embedded systems that don't have space for full operating system. But on computers, we do. We want to be able to run multiple processes isolated from each other in their own memory space. So the kernel needs to keep track of which process owns which bit of memory. To keep those records manageable, it doesn't keep track of every single byte. It keeps track of pages, which happen to be 4 kilobytes on my system. That's the minimum amount of memory a process can own. It cannot ask for less. Which has a fun side effect. If we look at a small executable like bin cat and do a hex dump of it, we'll see that a lot of it is all zeros. That's padding. When running an executable, different sections of it are mapped in memory with different protections like read-only, read-write, read-execute, and each section has to be page aligned. It cannot be smaller than 4 kilobytes. Or whatever the page size is. On Apple M1 and M2, it's 16. David Buchanan's quest for Netflix on his Hahi Linux goes into patching a 4 KB line executable to be 16 KB line. And if you're curious about how executables are loaded and run, you can read my series, Making Your Own Executable Packer. But pages don't exist just so that the kernel's internal data structures are smaller. They exist because the CPU itself is involved in memory address translation. Remember this image? See how it says 40 plus terabyte gap? I don't have that much physical memory, but that doesn't matter because we're looking at the virtual address space, which maps to a much smaller physical address space. Most of the time, when a program accesses memory, the CPU already knows how to translate from the virtual address to the physical address because the mapping is already stored in the TLB, the translation look-aside buffer. And this is really fast because the TLB is a cache in hardware directly inside the CPU. If it isn't in the TLB, then the CPU can walk the page table, which is in main memory, it's in RAM, so that's slower, but it's still pretty fast. And if it isn't in the page table, then it can cause an interrupt, which the kernel will have to handle. It's at that point that if the address is outside of what the program has mapped, it can raise a segmentation fault. But if it's inside of what the program has mapped, then it's merely a page fault. And the kernel can do whatever needs to be done. You can read from disk if it's mapped to a file, or you can return a page full of zeros if it's an anonymous mapping. So let's recap. Each process has its own virtual address space that can be much larger than the actual amount of physical memory we have. The CPU usually knows how to translate from virtual to physical address using the TLB and the page table, which means when switching from a process to another process, the TLB needs to be flushed, at least partially, or the translations would end up being all wrong. And this is an important part of the mental model you should have about memory. Addresses, or pointer values from one process, have nothing to do with addresses from another process. They live in completely separate universes. You cannot compare those in any meaningful way. You can share memory across processes if they both consent, but that just means that the same pages in physical memory will be mapped in different places of the virtual address space of each process. Again, the pointers will have completely different values, but they translate to the same physical memory pages. Everything clear? Are we good? Nah? That's okay, because it's time for some practice. We'll make a bunch of small programs and trace them with mevi and see what happens. Here's a program at startup. We can see it already owns some memory. The heap, which on this system tends to be at 5 something, is already over 100 kilobytes. And we also have a few pages over at 7 something. Cool. Let's allocate one vec of, let's say, 16 kilobytes. Ready, set, go. Nothing happened. I suspect the allocator already had a chunk of memory it was able to give out. However, if we allocate 10 more vecs of the same size, aha! Because these are small, the allocator chose to use the BRK syscall, the break syscall, to raise the program break, which grows the heap, and it places our vecs there. How do I know? Because if we then drop those vecs and call malloc trim, the allocator gives back parts of the heap, and you can see those regions became blue. That's where our vecs used to be. Those blue regions are still part of the process's virtual address space. They're just not backed by physical pages anymore. So they weren't unmapped. What happened was the allocator used the madvise syscall with the madv don't need flag to tell the kernel, I'm not planning on using these in the near future, you can do whatever with them. And the next time those addresses are accessed, there'll be a page fault and the region will become red again, it'll become resident again. And that's the difference between the virtual set, which is all addresses that the program could technically access if it wanted to, and the resident set, which is actually taking up physical memory. Here, the allocator explicitly gave up those pages, but sometimes the kernel makes those decisions. If there's not enough memory, it'll swap out some pages by writing them to disk, which frees up physical memory until the next time those pages are needed, and then it'll need to swap those in again. 16 kilobytes is pretty small, though. Let's try something bigger, like 32 megabytes. If we allocate just one 32 megabyte vec, it doesn't grow the heap at all. This time, the allocator chose to make an entirely new memory mapping with the mmap syscall. I can tell because it ended up at address 7 something. Interestingly, that new mapping is blue, which means it isn't resident yet. This is very much on purpose. Unless we pass the map populate flag to mmap, the pages we get back are faulted on demand, and that's called demand paging. If we start filling out the vec, we can see that our blue region gradually becomes red as the pages are faulted one after the other. And if we drop the vec, even without calling malloc trim, the whole region is released instantly, it's unmapped. So we got the basics here already. We can get pre-faulted memory by raising the program break with the break syscall or demand page memory with the mmap syscall. But in all our examples so far, we've pre-allocated the exact right amount of memory. What do you think would happen if the vec started empty and it grew as we filled it up? Let's find out. Well, it grows, but here's what I find interesting. Growing doesn't seem to cost that much. It's not allocating, say, double the capacity elsewhere and copying everything over. We'd see that happen if that were the case. Instead, it simply asks for a region to be made bigger. And that ends up moving it to another virtual address, but it's still pointing to the same physical address. So all the data that we previously had is right there, and there's no need to copy anything. Which is not the case with hash maps, for example. If we pre-allocate enough space for 100k elements, and insert random keys in there, we can see the hash map being filled randomly, which is pretty cool. If we then fill it beyond its initial capacity, it'll have to grow, and something very interesting happens. Did you catch that? Let's see it again in slow motion. When the table needs to grow, a new region is allocated, and data is copied from the old region to the new region, with 2 write heads at the same time, from right to left. And I couldn't explain it at first until I looked at the underlying implementation, and sure enough, at the time of this video, Rust's standard hash map type is re-exported from the hash-brown crate, which implements a Swiss table. These store metadata and elements separately, which explains the two write heads, and the Rust implementation chooses to go from right to left. I'm not sure why, but here's the code to prove it. There's a CPPCon talk that explains how Swiss tables work that I've linked in the description if you're curious. Speaking of being curious, before I show off mevi on some bigger programs and go into how I built it, let's hear a word from today's sponsor. This video is sponsored by Brilliant.org, the best way to learn math and computer science interactively. Whether you're looking to brush up on foundational math or get into some more advanced topics like AI, data science, or neural networks, there's a course for you on Brilliant. Maybe you're looking to make a career move, or maybe you just like to learn. After all, you're here now. Just wanted to show you this pleasant surprise as I went through the first course about how computers make decisions. We have a decision tree here, so it's not brown hairs. We go here, it's not black hairs. We go here, and we get completely the wrong result. And there's a whole section about how when computers make automated decisions but get it wrong, it can have real-world consequences. In computer science, it's not just about the what can we do, but also what are we going to do with it and what kind of consequences can it have on society. So I'm really happy that they cover that, and that makes me feel very good about promoting them today. Go to brilliant.org/fasterthanlime now to get a 30-day free trial of everything Brilliant has to offer. In addition, the first 200 of you to spring for an annual premium subscription will get 20% off. That's with brilliant.org/fasterthanlime. You can find that link in the description. The first big program I want to run mevi on is the one from Why Does This Rust Program Leak Memory? It's the reason I made that tool in the first place. Now what that program does is, given an original map of keys to values, it builds the reverse, a multi-map from values to keys. The catch is, the values in the original map own some heap allocated memory that we throw away while building the reverse map. It's like we're going from a hash map of key to tuple of value and bloat to a hash map of value to hash set of key. The program came with 3 different techniques for doing that. The first doesn't actually build the original hash map. It just builds the reverse on the fly from an iterator of pairs. Let's see what it looks like in mevi. Because we're building a large hash map, we can see the same grow then copy over with 2 write heads from right to left pattern that we've seen earlier. When that first technique is done, there's no extra memory used at all, so calling malloc trim doesn't make a difference. The second technique first builds the original map, so we're seeing a lot of allocations both via mmap for the hash map itself and on the heap for the bloat. Then we build the reverse map by iterating over the original map by reference, and finally we drop the original map. Once it's done, there's a lot of memory we can let the kernel reclaim, all of it in the heap. The third technique was the problematic one. Just like the second technique, it builds the original map first, but then consumes it as it's building the reverse map. So we have both allocations for the hash sets and deallocations for the bloat happening at the same time. It's not immediately obvious that it's problematic until we actually call malloc trim, at which point we realize that the hash sets ended up all over the heap, and it is now heavily fragmented. At last, we have visual proof. My previous video about this was, in fact, correct, and I'm as shocked as you are. Before we move on to bigger programs, I want to talk a little about how I built mevi. Truth is, I've been working on this for about a month now. I tried splitting off parts of it into other videos. A big part of mevi is ptrace, which we learn about in the strace feels like magic video. Essentially, mevi attaches to whichever process it's tracing and gets notified every time it's about to do a syscall. If it's a memory-related syscall, we need to update our internal state. We are basically keeping a simplified version of the same records the Linux kernel already had. The main data structure is range map from the range map crate, which handles cases like one big region splitting into 2 smaller ones when the middle gets removed, or many small consecutive regions merging into a bigger one. Most syscalls naturally map to inserting or removing ranges except for mremap, which is able to move a region somewhere else in order to grow it, and for which we need to copy over the state of every subregion. And that's just the backend. Because we want to visualize all that in a browser, the frontend also needs an up-to-date copy of the entire state. At first, I was sending the entire state every time it changed. You can see that in the building an htop like in your browser video, which was also preparation for this. That doesn't really scale though. It's a lot faster to only send diffs or operations and have both ends apply those to their copy of the state. But then the danger is, both copies can diverge if they don't apply operations in the exact same way. So I went with Rust on both ends. That way the front end and the back end can share some code in the mevi common crate. We share an event struct, we share enums, the range map type, U64s everywhere. And the events themselves are serialized with postcard, a high-performance binary format originally designed for embedded stuff. The backend is built with cargo as usual, and the front end is built with trunk, which works exactly as advertised. It builds Rust code into WASM, along with some HTML and JavaScript boilerplate that we need to get everything to load properly. Trunk also acts as an HTTP server and even reacts to changes in the source code to rebuild it and reload the browser. It also has support for WASM opt, which shrunk the WASM bundle from half a MB to 370 kbs or about 130 kbs gzipped. I've honestly seen bigger React apps than that. Performance was a challenge. Every single region is a DOM node, so the browser slows down significantly when showing a fragmented heap. We might be better off with something like Canvas or even WebGL, but I did two things that helped performance significantly. One, when there's a lot of regions, just don't render the tiniest ones. And two, buffer events on the backend so that even if a few thousand events happen, the front end only updates its state something like 30 times a second. Despite my best efforts, mevi still slows down some programs significantly, which is not surprising once you understand how it works. You gotta remember that every time a trace does a syscall, it's stopped and waits for the tracer to resume it. So there's some overhead inherent to ptrace even if you're just immediately resuming the trace. But that's not even the real reason. The real reason is that to be able to show those red regions here, to know which ones are resident, we have essentially three options. The best one is probably eBPF, but I want to keep that for another video. You can also read from procfs every so often. For every process, there's an smaps file that has every region along with how much of it is resident, but you don't get as much detail and it's not real time. The option I actually went with is userfaultfd, and that's not what it was made for. Imagine you're a cloud hosting company. You have machines that run user applications. Ideally, those applications should only be stopped or restarted when the customer says so, but you also want to be able to retire machines sometimes. The lame way is to tell your customers, okay, your stuff's going to restart on that day, so just, be prepared. And the cool way is to tell your customers nothing and transparently move their application while it's running to another machine, and that's called live migration. There's a couple ways to make it work, but eventually the app is running in the new location, even though some of the memory is still at the old location. Userfaultfd lets you register virtual memory ranges for which you want to handle page faults in user space. So when the app tries to access some memory that hasn't been copied yet, it gets stopped. And from another process, you can be notified by reading events from the userfault file descriptor, that's what the FD stands for, and then decide how you want to handle the page fault in userland. You can copy from another page, or you can zero out the page, which is what mevi does. And that's how mevi knows what's resident. Thanks to ptrace, it knows the virtual memory layout of the process, registers those regions with userfaultfd, then gets to handle page faults itself, and that's also why it's slow. We now have two mechanisms that stop the tracey, one on syscalls and one on page faults. Now, I know I'm making this all sound easy, or am I? But it really wasn't. We've already seen in the strace video how to start tracing a process by calling traceme between fork and exec. So it's already a new process, but we still have control over it. And I thought I could do the same with userfaultfd, but exec completely changes the virtual memory layout of the process. It's replaced by a new executable. And the userfault file descriptor still points to the pre-exec virtual memory layout. So anything we do with it will just return an error. So userfaultfd needs to be set up after exec. First, I tried what every memory provider is doing, like memusage or bytehound, make a dynamic library that has an initializer function and inject it into the tracee by setting the ld preload environment variable. That works for simple programs, but not for those that fork, but then never exec. Chromium does that, for example. It has a zygote process that serves as a template that's forked every time it needs to make a new renderer process. This saves time and memory. Now you can subscribe to fork events through userfaultfd, but that requires the sysptrace capability, which essentially means you'd need to run the tracee as root, and that wasn't acceptable. Don't run browsers as root. That's a really bad idea. Another problem with LD preload is that sometimes the dynamic linker will just refuse to inject your library if the target's running in secure execution mode, for example. Also, the tracee could just unset that variable. It's not a reliable way to inject into everything. ptrace, however, lets us not only intercept syscalls, but also do anything with the tracee at that point. So I ended up using ptrace to do the userfaultfd setup. which is honestly not that bad. You pause on sysexit, you set the registers to whatever you need them to be, rewind the instruction pointer by 2 bytes, the size of a syscall instruction, resume until sysenter, resume until sysexit, and repeat for any syscalls you need to do. And before letting the program resume for real, you restore all registers to their original state. Except, you know how virtual memory means something different for different processes? File descriptors are the same way. File descriptor 0 in process A is not the same resource as file descriptor 0 in process B. And we have to set up userfaultfd from the tracee, but we need to control it from the tracer. So our only option here is to send the file descriptor across processes. One way to do that is to have the tracer listen on some Unix domain socket, and for the tracee to connect to it and use SCM writes to transfer the file descriptor over. This is already annoying to do normally, but doing this through ptrace was even more confusing. I discovered only while writing the script for this video that there's a much simpler way to do this with pitfd, but again, that could be its own entire video. Even after all of that, I ran into some problems because both userfaultfd and ptrace can report some of the same events, but not always in the same order, which ends up making mevi's view of memory inconsistent. But I'm happy to report that I got it running on some real-world programs. Here it is running on cargo install. The overhead is incredibly high, but you can see processes come and go as rustc builds individual crates. We can see C compiler invocations, linker invocations, everything. That's pretty fun. I really wanted to use mevi on a browser. Chromium didn't work out, but I did get it working on Firefox. Not the snap version, there's a sandbox there, but we really want to disable all the sandboxes. We don't want any setuid binaries. We don't want any self-tracing processes. We don't want PID namespaces. We don't want seccomp BPF. But yeah, I can load a couple sites and see that each tab is its own process. Or maybe it's each origin, I'm not exactly sure. Loading a heavy site makes memory go up, closing a tab makes memory go down, so that's good enough for me. It might not be enough for another man, a greater man, but for me, it's enough. Mevi is open source, it's dual licensed as Apache 2 plus MIT, so you can go ahead and play with it. The GitHub repository is in the description. Do keep in mind, I don't really plan on maintaining it. This is a research project, so if you want to use this for anything serious, you should probably maintain your own fork. Thanks to Brilliant.org for sponsoring this video, and all of you on GitHub sponsors and Patreon for making this work possible. Extra special thanks go to Lorenzo Stokes, who helped me with this video. Lorenzo is a Linux kernel contributor, and he's writing a book called The Linux Memory Manager. You can find the link in the description, just like with all the other links. I really appreciate being able to move around and tackle different topics, so thanks for backing me on that. Another audience, a lesser audience, might have problems with that, but not you. Oh no, not you. Alright, I'm out. Peace.